Okay, so for the first part of homework 7-3 here, got a few multiple choice questions to get through. So the first one, we've got a ball that's rolling down a ramp, and at first it says it does not slip. And keep in mind, when it says it doesn't slip, what that really is telling us is this is going to rotate, right? So this is going to cause the ball to rotate. Then on the other side, it's frictionless. And because it's frictionless, the rotational motion won't be changing, right? There's nothing that's resisting that rotational motion, so it won't change. So then they give us the following options. Which maximum height does it reach? Right, on the frictionless side. Does it go to a greater height, lesser height, same height, impossible to tell, and then impossible to tell without the radius or the mass? Well, the first thing, hopefully, that we can rule out pretty quickly is if it's starting from rest, if it's released from rest, there's no way that it's going to reach a higher altitude than when it was released, right? There's no way, if it's only starting with potential energy, there's no way that it can then reach a higher altitude than that starting point. So we can pretty safely rule out option A. So then the big question becomes, is it going to be a lesser height or the same height? Well, in order to be the same height, right, think about what would happen. As the ball rolls down, I know it's starting with potential energy. As it rolls down the ramp, because it is rolling, that potential energy goes to both rotational and linear kinetic energy. Right? It goes to both rotational and linear kinetic energy. So some of it goes to linear, some of it goes to rotational. Once it hits this point on the ramp, once it hits that frictionless part, the rotational motion is not going to change. And so the significance there is, as it then continues to rise back up, that rotational kinetic energy is actually going to remain constant. So if we think about that, so again, I go from potential energy to each of these, right? I go to each of these, and then on the way back up, the only form of energy that changes back to potential is just this one, right? So that one goes back to potential energy due to gravity. But this energy here does not change. So, for example, if I threw some numbers in here, I'd maybe start with 10 joules of potential. After it rolls down the ramp, maybe 2 joules are rotational and 8 joules are kinetic, right, linear kinetic. By the time it goes back up the ramp, only those 8 joules of linear energy are going to transfer back to potential, which means it's still going to have 2 joules of rotational kinetic energy. So the significance of that is it is going to rise to a shorter, a lower height than it initially was dropped at. And this is a question that obviously the more we deal with the rotational motion, the better hopefully you get with it. But it does not reach the same height. It would reach a lesser height because on that frictionless surface there's not going to be any friction to cause a change in rotational motion, and so that rotational kinetic energy would remain constant as it rises back to that new height. Question 2, a very conceptual question, but one we do want to make sure we're comfortable with. And this is one that you should be comfortable answering without using the equations for the moment of inertia. So you should be able to kind of reason your way through. So they ask us which one has the greatest moment of inertia about the axis in the middle. Right? So which one has the highest moment of inertia? And again, the big concept is the moment of inertia is the sum of all of our masses times the radius squared. Right? So for any of these objects, the moment of inertia would be the sum of every mass times the radius squared. And so we're looking at what factors influence the moment of inertia being higher. Well, the higher either the total mass or the higher the radius, right, that's going to make the moment of inertia higher. They told us that each of these objects has the same mass, so we know that that's not really going to come to play. So the biggest question is going to be which of the objects has the most mass located the furthest away. And hopefully as soon as you make that realization, it's pretty easy to choose option B here. Right? If I look at the options A and C both have mass kind of dispersed throughout the disk, right? So some of the mass is very far away, some of the mass is very close to the axis of rotation, so its moment of inertia is going to be, again, we know that's at 1/2 mr squared, but it's going to be kind of somewhere between the full distance and the minimal distance, right? For the wagon wheel here, most of the mass, now they do have the spokes, but we'll assume that there's not a lot of mass in that. Most of the mass of this wheel is going to be accumulated the full radius away. Right? So if I take all of those masses and multiply them by r squared and add them all up, this one's going to have my highest moment of inertia because all of that mass is located as far away as possible. Right? Object D is obviously going to be somewhere in between B and C or B and A. And as I look at that, right, it does have some mass collected towards the center, but it also has some mass out further towards the ends there. So anyway, object B is the object with the highest moment of inertia. And I do want to make sure everybody's feeling pretty comfortable with how to figure that out, right? Again, regardless of whether we have equations or not. Question 3 is actually exactly like question 8 from homework 7-2. The only difference on this is this one actually gives you multiple choices to choose from, right? So it's the exact same question. This one just gives you some options to choose from. So I may not go into a whole lot of detail with that. If you do need to go back again, reference question 8 on homework 7-2, and this will give you a little bit more detail with that. But all you're doing is you're finding the moment of inertia for each, and so really, again, the only thing I'm going to touch base on is for when it's at the 50 centimeter mark, I'd be finding the moment of inertia of the center of mass, which for a rod, for a thin rod, would be 1/12 mr squared or ml squared, right? And then for finding the moment of inertia at that second rotational spot, so at the 30 centimeter mark, I would be using my parallel axis theorem, which says the moment of inertia equals the moment of inertia about the center of mass plus the mass times d squared, right? So I just find these two measurements, and then when I find those, I end up getting a ratio of about 37 to 25. So then obviously if I approximate that as a decimal, that ends up being about 1.5 as the ratio between the moments of inertia. So again, like question 8 from homework 2, if you need a more thorough explanation, feel free to go back and consult that video. But I don't want to waste your time here, so I will probably leave this explanation at that, and then just have you reference the old question if need be. Okay, question 4 here has to do again with rotational kinetic energy. So it has to do with rotational kinetic energy. And the equation for rotational kinetic energy is just very similar to what it is for translational. It's 1/2, but instead of the mass, I use the rotational equivalent, so the moment of inertia. And instead of the linear velocity, I use again the angular equivalent, so I use my omega squared. Right, so this is the equation that we're referencing. So they give us two different shapes. They tell us they have the same mass and the same radius, and then that length of the radius actually doesn't matter for that cylinder there. It doesn't matter how deep the cylinder is, if you will. That doesn't actually come into play. But anyway, what must be the angular speed of the cylinder so it will have the same rotational kinetic energy as a sphere? So we want the sphere and we want the cylinder to have the exact same kinetic energy, right? So we know that ultimately we're going to want these two measurements, these two values, to be the same. So if I look at this, well, again, 1/2, what is the moment of inertia for a solid uniform sphere? Well, the moment of inertia, that goes to the equation sheet if you look it up, right? But it's 2/5 mr squared. So that is my moment of inertia for the uniform sphere. So, and then they said we're going to relate this to the angular velocity of the sphere, right? So we're going to relate it to the angular speed of the cylinder, relating that to the sphere. But anyway, so I've got that. And then again, I want this to be equal to the kinetic energy of the cylinder. Well, the kinetic energy of the cylinder would be 1/2 the moment of inertia for a cylinder, which is 1/2 mr squared, right? So I've got that, and then again, I'm going to call this maybe omega 2 squared, just so I don't get that confused with the one for the sphere, right? So the omega of the cylinder in terms of the omega, the angular velocity of the sphere. So if I start looking at this, well, there's a lot of stuff I can cancel out, right? The 1/2s I can get rid of. They both have the same mass, so I can get rid of that. They both have r squared with the same radius, so I can get rid of that. So this does simplify pretty nicely. I get 2/5 omega squared equals 1/2 omega 2 squared. So then obviously if I'm solving for the second velocity in terms of the first one, I'd multiply both sides by 2, so I get 4/5 omega squared equals my second one, right? So then if I square root both sides, this will give me my answer in terms of the original one, right? So I get my second angular velocity. The angular velocity for the cylinder would be the square root of 4/5 and then times the square root of the omega squared here. So that is included underneath square root. So if you simplify that, right, if you do just a little bit of algebra to clean that up, square root of 4 is 2. The square root of omega squared is omega, it's w, and then on bottom I have a radical 5. So notice they didn't rationalize the function, and that's perfectly fine. But the correct option here is D, right? The square root of 4 being 2w, and then the square root of 5 on bottom. So all we really did is the biggest step here is being comfortable with what the rotational kinetic energy is, and then relating them together for the two equations here, and then finding your second velocity in terms of your first one. Okay, so question 5 is another one that will take advantage of energy's force here. So while spinning down, I assume they're meaning slowing down here, but while spinning down from 500 RPMs to rest, a solid uniform flywheel does 5.1 kilojoules of work. If the radius of the disk is 1.2 meters, what is the mass? So they are telling me, if you're not sure what a flywheel it is basically a cylinder or a disk. It is a solid uniform disk, so we know then the moment of inertia would be 1/2 mr squared, right? So we've got our moment of inertia to work with. And then it's going from 500 RPMs to rest, and it does this much work. So the key concept here is, obviously, as always, the work is going to relate to any change in energy. So in this case, in kinetic energy, right? So again, I'm just going to take advantage of whatever work I've done that's going to cause my change in kinetic energy, right? That's going to relate to it. So all I really have to do is I have to find my change in kinetic energy using my work, and then relate that to my moment of inertia as well. So let's start by finding our initial velocity, right? It is 500 RPM, but I need, instead of revolutions per minute, I do always need radians per second when I'm doing any types of calculations using energy or kinematics or anything like that. So revolutions per minute, and then again I need to convert that to radians per second. So 1 revolution is obviously 2 pi radians, and then 1 minute is 60 seconds, right? So 60 seconds. So anyway, calculating that, we end up getting about 52.36. If I round that off a little bit, and that's fine to do so, but I'm going to round that off at about 52.36 radians per second. So I've got the initial angular velocity, and then I know it ends at being at rest, so its final angular velocity would be 0. So then they give me the amount of work, 5.1 kilojoules, so keep in mind that would be 5,100 joules, right? So that's how much work I've done. So then really, if I bring this all together, again, the amount of work, 5,100 joules, would equal my change in kinetic energy. So my final kinetic energy minus my initial kinetic energy. Well, my initial kinetic energy would be using this velocity, and my final one would be 0, right? And so in this case, they do say there's this much work done on it. Obviously, if you look right now, it's going to look like it's a negative number, but let's just focus on that being the change. So we know that this is how much work was done on it, which technically would mean that's a negative amount of work done on the sphere, on the disk, to take away that much energy. So we are really just going to then worry about the magnitude of this. We don't have to worry about the fact that it was a negative quantity for us. But anyway, getting past that. So 5,100 joules of work done on this. Again, the amount of kinetic energy it starts with, well, kinetic energy is 1/2 I omega squared. I just found my omega, right, my 52.36. That is my starting velocity. And then again, I for a uniform disk is going to be, the I for a uniform disk is 1/2 mr squared. So at this point, if I just break the equation up, I know all of the values except my mass, right? So it's 1/2, and then I plug in, I substitute in for the moment of inertia, so another 1/2, the mass, which I don't know, the radius, which is 1.2 squared, and then the omega, which is 52.36 squared. So I've got that in there. So really, again, plugging this all in, setting it all up, I just have to then solve for my mass, right? So all I have to do then is solve for my mass. So when I do that, calculating this out, I end up getting about 5.17 kilograms. Right? So my mass of the wheel, 5.17 kilograms. So then the last question for this part, question 6. We've got a softball player swinging a bat. That bat, as it's being swung, is going to act as a uniform rod that's being accelerated, that's being rotated around the end pivot point, right? So it's going to act like a rod that's being pivoted over here. So the significance of that is its moment of inertia for a rod, if it's being pivoted about an end point, would be 1/3 mass times the length squared, which we've seen before. So they give us enough information that I can then go ahead and calculate my moment of inertia, which I may or may not need later, right? So 0.90 times, again, the length of it, which they give me as 0.95. So squaring that. So I get my moment of inertia to be 0.27075 if I take that out to a few decimal places here. So then they're asking me how much torque does the player need, right? Well, torque equals the moment of inertia times the acceleration, right? The angular acceleration. Again, I just found my moment of inertia, so no big deal. So all I have to do then is a little bit of kinematics to find my angular acceleration, right? So starting at rest, I know my initial angular velocity is 0. My final angular velocity is 2.6 revolutions per second, but I do want that in terms of radians per second. So I'm going to go ahead and multiply that by 2 pi. That gives me about 16.3. And then the time obviously being 0.20 seconds. So then if I use WOTAT, if I use my angular velocity as a function of acceleration and time, then I find my acceleration to be about 81.7, and I can plug that in here along with the moment of inertia, and that's where we should get 22.1 Newton meters of torque.